learn relativity. So, you may be wondering why I started one more channel when I had already had. Welcome to my new channel. My new channel is called, uh, this is channel is on relativity. The channel's name is Let Us Learn Relativity. As most of you know, I already have a channel by name Physics Maths Made Simple but Not Simpler. But then my aim in starting this old channel was to basically learn the necessary math and physics to understand the latest theories of everything, those, and it was taking very long for me to go through all these necessary math and leave alone physics. I haven't even touched upon physics yet on this channel. It is taking very long to uh, learn basically the essential physics. So while continuing with this old channel, this deals with teaching, basically learn and teach physics and maths, the necessary physics and maths. This channel will be dedicated to learning relativity, which is my ultimate goal. Uh, so, what is the best way to learn about relativity? Of course, learning from the best, the very creator of theory of relativity himself, Dr. Albert Einstein. So, we will be uh, basically referring to this book, The Principle of Relativity by Dr. Satyendra Nath Bose. Not many of the present day generation in India know about Dr. Satyendra Nath Bose, but he was a close associate of Dr. Albert Einstein, and in fact, uh, Dr. Bose, the boson, what we know as boson, is named after Dr. Bose. Bose is named boson. We all of us know we know the bosons W, Z, and Higgs, right? These bosons, the very term boson is named after Dr. Bose. So we'll be learning. Uh, this is a book. The principle of relativity is written by Dr. Satyendra Bose. So it contains the original papers translated into English from German. Okay. So who did this? The, the translation from German was done by Dr. Bose himself and one more of his colleagues, Dr. M. Saha. And the foreword was given by Dr. Maha no Balis. Rather, Maha, Mahala no Mahala no Bis. Bis. Mahala. Mahalanobis. Though I am an Indian, I too this name is a bit difficult for me, even for me to pronounce. So anyway, so these are the stalwarts, the uh, people who were there with Dr. Albert Einstein when he came up with his papers. So it's a shame that present day generation doesn't know much about uh, Dr. Bose. Is one of the best uh, professors. I mean, physics professors of Indian origin. He worked in US, of course, but still his origin is India. He was the best professor. I think, according to me, there were only very few guys who got Nobel Prize in physics. Uh, One was Dr. C.V. Raman, then his nephew, grandnephew, or someone, Chandrasekhar, after whom the Chandra laboratory is named after. Raman, Dr. Raman is not himself, Raman effect. So the contents of this book are introduction by Dr. Mahalo, Mahalo, Nobis, Mahalo Nobis. This is something like we we have in Hawaii. They have this word Mahalo. Mahalo is a kind of hello, I think. So anyway, if you remember that Mahalo, then you can pronounce this name easily. Mahalo Nobis. Now, second, after introduction, the second part will be on electrodynamics of moving bodies. So this is the original paper uh, by, of course, Dr. Albert Einstein. In 1905, he submitted this paper to magazine called Anna Land, Physics, uh, which in German is Annals of Physics. That this translation, this paper's translation is made by Dr. Um, Meghnad Saha, M.M. Saha. Okay, so this is the first part we are dealing. Apart from introduction, this is the first part. The second part we'll be dealing with is, uh, of course, a short introduction, um, biography rather, of Dr. Albert Einstein by, again, with the translation of the same guy who translated this paper, M.M. Saha. Dr. Saha. Third part will be, yeah, the very principle of relativity. This by uh, H. Minkowski. His original paper. This is his original paper published in 1909. Again, the translation, again translated by M.N. Saha. This is the paper by original paper submitted in 1909 by Hermann Minkowski, and the fourth part is, there's an appendix. We'll not consider that. The, of course, the generalized principle of relativity. This is the original paper submitted in 1916 by Albert Einstein, original paper, and translated by Dr. Satyendra Bose. So, briefly, this is about the book and the contents we are going to learn. I mean, contents we are going to uh, basically go through. And now let us proceed to the, what do you call, introduction. Introduction by Introduction was given by Dr. Mahalo Nobis. right? So now, what is the uh, background of creativity? Why we actually came up with, well, Einstein came up with relativity? At around 1895 or so, Hertz, Hertz came up with a theory that plenum, there is something called like plenum, which is one ether for light, heat, electricity, and magnetism. Right. And after that, 10 years later, in 1905, Albert Einstein came along and said, quote, the ether will be proved to be superfluous, meaning ether will become redundant. There is no such thing as ether. The relative motion between the bodies doesn't need ether. Earlier, they thought the plenum, the, the whole, what do you call, manifold, and the whole, basically, uh, yeah, a whole manifold, let's say plenum, and then everything. Uh, Ether is needed for light, heat, electricity, and magnetism to travel in the undulate, basically. Where does, how does light come, and what does light interact with? They thought that the ether, there is a omnipresent fluid called ether, because of which, in which all these uh, types of energy, um, forms of energy float and interact with each other. But here, ether, Albert Einstein in 1905 came along and said the ether will be proved to be superfluous in the sense ether is not real. That was a very bold statement. But then, what was the background for this? Uh, in 19th century, there was a guy called Young and his friend Tesla. They came up with wave theory. Wave theory, excuse me, the innate stationary aspect of elastic solid. Let's say this ether thing, they thought like a kind of a jelly-like thing, which is needed for these waves or the uh, particles, maybe whatever later they were found out to be, to play around in. They thought this was a medium in which they were doing that. So, the stationary aspect of elastic solid was outcome of research for a, a medium in which the light waves could undulate. So, in this ether, the light waves could undulate. Light waves, for that matter, electric waves, electromagnetic waves. That's what they thought. But then, what happened? That was the first time anybody thought about relative motion. This ether was in the background, and these particles, these waves, the light, heat, electromagnetism were actually undulating in the background of ether. But then what happened was, then came along another guy called Arabu. Arago, what he did was he was experimenting with the refractive index of glass. Right? When you want to know something about light and its behavior, naturally you need to know about the refractive index, right? How why the rays of light are bending inside water. That's a common phenomenon. We all observe that, right? When light enters the water, the objects inside the water look somewhat away from their personal position, right? So Arago's prism experiment, what he did, so uh, let us say he took up the prism. The light is incident like this. That's the direction of light, but it refracts. It should have gone like this, right? But it took a turn, some theta, let us say from here to theta. This is the incident angle. This is the angle with which it refracts. We call this basically refraction. So this there's a term called refractive index. This refractive index depends on the incident velocity outside the prism. This is incident. This is the velocity inside medium, right? Fresnel fixed ether hypothesis. Uh, if let us say Yeah. On Fresnel's fixed ether hypothesis, this is the incident light waves are situated in the stationary ether. Let us say Fresnel's waves were situated inside ether, right? Inside ether, the light was traveling. Stationary ether. And this prism was moving with a velocity of u, rather c, with the c, with c with respect to ether. This is the background ether, and in the ether, with respect to ether, these rays, this these rays move with the velocity of c, right? If prism itself, these are, let us say, c, like first they were moving with c, this prism itself is moving with u, let's say. So what will should be the resultant velocity should be c plus u, isn't it? Thus, the refractive index of a prism will depend on u. Refractive index Ri should depend on this u, right? But let's see. The surprise was a pleasant one for some, not for others. The upset due to elasticity of the prism. Arago performed experiment in 1819. What happened was the surprise was failed to detect change. Meaning, though they were expecting it to move, light to move with C plus U, this is elasticity of C plus U, Ar, uh, Arago, right? His name is Arago. Arago. Arago in 1890 conducted an experiment and he failed to detect image. Meaning, whatever you do, it was not changing. Irrespective of the medium, it was not changing. Then came along the guy called Airy Boscovich, Bosovich, right? Bosovich. What this guy did in 1766, when you look down from a telescope, what he thought was the light coming from here it changes with this refractive index of medium through which it is traveling. And he filled this telescope with water. He filled the telescope with water and watched this, and still he could not. The average relationship did not change. So even here it failed. Meaning any experiment supporting existence of ether failed. That's the bottom line. Then Then, uh, then again, Fresnel again, Fresnel came up with a con, uh, convection coefficient, which is 1 by mu square, mu e, where mu is refractive index. So he came up with ether convection theory. According to Fresnel, the presence of what he proposed was presence of matter implies a definite condensation. What basically he was saying was this ether is like that, fluid ether. When you drop a mass here, this presence of this matter will basically, this is like a viscous, ether is like a viscous liquid, fluid rather, and that fluid, that it's it will get condensed. See, let's say the layer of the ether was like this before dropping this mass. Then after dropping mass, what it becomes is it becomes less dense. Sorry, the, uh, uh, definite condensation. So it will basically this ether will be like this ether will become like this, condensates, compactifies rather. So that's what Fresnel told. And whatever material, if you take this was like this, and it got condensed like this, and this minus this is some liquid, some fluid, rather ether, got away, right? Carried away. So this excess portion of ether is supposed to be carried away with its own piece of moving matter, meaning this whatever because of condensation, whatever ether was displaced from here, this will go away with another its own matter. Let's say matter ether. While the rest remains stagnant as well. This portion will remain stagnant as well. This portion alone will go away. So, as we know, uh, next came along Stokes. Were all wonderful geniuses. He proposed the existence of viscous ether. Viscous ether When Fresnel told this will remain stationary, small portion which is displaced will go with its own mass. But what Stokes, I mean, the onus is on the word stationary. Ether was stationary. But Stokes came along and yeah, what he said was he tried with a viscous material. Viscous motion ensures near the surface of the separation. When you drop it here, at the separation of surface, viscous motion takes place. And the moving matter. The surface of this moving matter as well as the rather boundary. Here, viscous motion takes place. Elsewhere, it is stationary. Again, stationary. Only the portion where it is in contact, that portion will experience viscous motion. But he still supported that this what do you call Fresnel's 1 minus 1 by mu square still holds. This is what he was compelled to say. The two were pretty much similar, only that here this is viscous and here there is no mention of viscous matter there. Now, now came along another guy called Fritzsche. Now, another guy called P, Preview. Preview conducted an experiment in 1851. He conducted an experiment which was which met with grand success. What was his experiment? His experiment was if a divided beam of light, if a divided beam of light is reunited after passing through two adjacent cylinders filled with water, let's say, ordinary interference patterns will be observed here. ordinary interference patterns will be observed, produced. If the water in one of the cylinder is now made to flow, let's say this is made to flow, the condensed ether within the flowing water would be convected and would produce a shift in interference phases. So if this is made to the water inside this cylinder, one cylinder uh, is made to flow, then the condensed ether within the flowing water would be convected and would produce a shift in the interference. So naturally, if there is ether, this ether would should have, if it is condensated as Fresnel expected, this condensated ether should have pushed this and should have created a different pattern of interference. The shift actually should be k equal to 1 minus 1 by v square. That should be the corresponding, I mean, it should be proportionate to that. So, naturally, as they found the proof for Fresnel's this thing, when this proved to be true, then everyone was, I mean, thinking, thought, uh, okay, ether is here for an order. But all such attempts, uh, on the other hand, negative evidences in favor of convection coefficient also have multiple. Who did this? Mas, Muscat, Oak, Maxwell, my favorite scientist, and others sought definite changes in different optical events induced by the motion of Earth relative to the pulsation. So, all of expected, these guys expected what changes uh, in different changes due to Earth's motion, Earth's motion relative to ether. So, if everything is according to plenum, this is plenum, let's say, the manifold containing everything. In this plenum, Earth is also a part, right? This Earth is moving in this plenum. This is filled with ether. So, Earth's movement through ether should have produced some, what do you call, condensate, right? But all such attempts failed to reveal even slightest uh, trace of optical disturbance due to the absolute velocity of that. Though Earth is traveling at 180 mi- mm, miles per second, right? 1000, 18 followed by 5 zeros, I think. That should be right. The velocity of Earth. So it is moving with such a great speed, velocity, but it didn't have they couldn't observe any change due to the Earth's movement through it. No evidence was found. Anyway, now the most important, as we have seen, this was a kind of a war between those who believed in ether, existence of ether, and those who didn't believe in the existence of ether. So what happened? Yeah, though there were some uh, uh, proofs that this viscous ether, viscous or we can viscous motion or condensate going away with its own mass. Uh, for all those, though they kind of found some uh, 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 support, they found some support, no doubt, but uh, ultimately they couldn't find proof, solid proof that ether indeed does exist. Then the most important thing in the history of ether happened. What happened? Then came Michelson and Morley in 1881. Michelson and Morley conducted experiments. They sent a wave. This was one mirror, and this was one mirror. They sent a wave light here, put a torch here, this light comes here, and it goes back. And if you move this somewhere here, it should have been incidents, something like this, came out like that. And after doing all those experiments, they couldn't find difference in velocity of light. It should take less time to travel from here and go back here. And it should take more time to travel from here and travel back to here if it is moving, right? But still, they couldn't find any difference at all in the velocity of light. It remained constant. This is the most uh, the what do you call the experimental result which necessitated necessitated the constancy of light, meaning light traveling with velocity of c never changes. That remains same. Whatever we do, whatever whether these observers are moving, the observers are not moving, the constancy of light is maintained. I mean, not observers moving. This is all about stationary observers, stationary in the sense. This is the This basically later it becomes what do you call the special special relativity. The fundamental postulate is that velocity of light remains constant; it doesn't change. So there was one more scientist called Eddington who wrote a book on relativity. He uh, gave an example for this, right? A, the position O, B, U. Let's say there is a guy who is swimming from one guy. Let's say the one guy is swimming. Two examples he took. One is swimming along tide, along what do you call it, stream. Second is swimming against tide, against stream. Okay. So if then we divide a beam of light into two parts, send one swimming up the stream for a certain distance, basically light. Let us say two beams of light we take. One is swimming um, along the tide, the other is swimming against the tide, upstream, let's say. And then they are reflected back. Okay, so what will happen? The let c be the velocity of light. The time of double journey along OA, along OA, along OA, it should have taken time t1 is equal to L by C minus U plus L by C plus U, because while he was going from uh, um, here to here OA, he would have taken so the velocity of light is c, and if he is swimming with u, then what happens when he is going against along the tide, it will be added. When he is going up against the tide, it will be less than that. So it will be 2lc by c square minus u square, or 2l by c beta square. Right? For the transverse journey, the same thing. For the transverse journey, same thing would take uh, T2, T2 transverse equal to 2a by root c square minus b square equal to 2 alpha, I think, alpha, 2 alpha by beta What does that mean? Earlier we had 2L by C beta square for a long string. This is how much the same L. Yeah, this is beta square. Yeah. This is beta, meaning T1 obviously T1 is greater than T2, right? T1 is greater than T2. The time taken for uh, mm, that T1 should have been greater than T2. Yeah, that going by this calculation. But instead, it was found that they were same. The what do you call same time. T1 was equal to T2, meaning the light travel. There was no such thing as C plus U or C minus U. It always traveled with C. That was the confirmation that the speed of the velocity of light does not depend on anything, it is constant. So that became the building block for of special relativity. Right. Then the relative motion of ether and matter from the point of electrical theory. Then came along Maxwell. Maxwell conducted experiments on electricity and magnetism, and he concluded. Then came James Maxwell. Maxwell's displacement current theory hypothesis. Displacement current theory hypothesis he proposed. This the static solid ether beam, according to his theory, the solid ether beam became, is very, very important. Um this is the basis for actually Einstein's theory. Einstein's theory was based on two basic principles. One is principle of equivalence proposed by Galileo, and then the this Maxwell's electromagnetic theory. So this solid ether became gradually transformed rather became transformed into electromagnetic wave. All of a sudden, there was no ether The very same thing they were calling ether transformed into electromagnetic one. So Hertz experiments in 1886. In 1886, Hertz experiments confirmed Maxwell's theory. Electromagnetic, right? Electric waves, electric waves behave exactly like light waves of large wavelength. Only difference is large wave. Electromagnetic waves behave exactly like light waves, but of large wavelength. Yeah. And then came along J.J. Thomson. J.J. Thomson's work on electrons. J.J. Thomson's work in 1880. J. J. Thomson, who is famous for uh, discovering electrons. What his experiments proved was that instead of 1 minus 1 by mu square of Fresnel's refractive, the static ether thing, convection coefficient. Convection coefficient came out to be, instead of this, half. J.J. Thomson proved it. This obviously implies a complete failure to account for all optical experiments which depend on their satisfactory explanation, assumption of the value token. This. So everything which was based on this assumption that the convection, what do you call it, convection coefficient was wrong. This was proved wrong. J.J. Thomson drove the ultimate final nail into this theory of ether. The modifications, some guys like Hertz and Heaviside tried to still support this thing, but all their efforts failed. They postulated actual medium to be seat of electrical polarization and further emphasized reciprocal relation between electricity and magnetism. Now, according to Hertz, a moving dielectric would carry away the whole of its electric displacement with it. Hertz proposed that The moving dielectric would carry whole of its electrical displacement with it. If it is going like this wire, it carries all its uh, electric displacement with it. So he said it will be proportional to K. What is K? The uh, the specific inductive capacity of the dielectric. Specific inductive capacity of a dielectric. And then came along H.A. Wilson, who proved that it is not indeed proportional to K, it is proportional to K minus 1. So many twists and turns in the story. Yet, but what we need to remember at the end of the day is that ether, there is no such thing called ether. And uh, uh, so it was clear that Lorenz also Lorenz also had a say in this. He conducted experiments. Lorenz, of Lorentz transformations, also conducted experiments, and he assumed that moving dielectric merely carried its own polarization doublets, which in his theory gave rise to the induced field proportional to K minus 1, not to K. He gave satisfactory explanation of all that, so supporting that they are indeed proportional to K minus 1, not K. Further succeeded in explaining values of representation, which to yeah. So coming back to um, Michelson-Morley experiment, and we saw that 2L beta square is one thing, and to the other was 2L beta. So T1 was greater than T2, right? So at the end of the day, what Lorenz did, Lorenz was smarter than many of his contemporaries. So what he did was he came up with transformations. Whenever you say the word Lorenz, you take the name of Lorenz, that the, what comes immediately to your mind is transformation, right? Lorenz transformations. So he came up with a special set of transformation equations for time, which implicitly introduced a concept of local time. He came up with transformations, and he implicitly introduced time. implicitly introduced the concept of local time. So he proposed local time instead of the universal time against universal time, which was in practice till then. He proposed local time. But then it was just a mathematical tool that he used to support his theory. The yeah, then of course they came the ultimate genius, who is the anyone who is into physics, maths, would agree that Einstein is basically the the genius, the ultimate genius so far. Uh, of course, there are so many great scientists like Newton, Kepler, Galileo, and all the old scientists, the mathematicians like Euler, Leibniz, and all. Einstein is, of course, the best. Then came Einstein. He, what he did was, his greatness was, he he thought all these concepts, this uh, light, heat, electromagnetism, all of these things, and ether, in respect of ether, he provided physical interpretation, physical interpretation for all these things together. And he said there are coherent, organized consequences of a single general principle. They were thinking electricity was different, light was different, electromagnetism was different. All these were different. They were thinking so far, but Einstein came along and said, "Oh no, all of these are one single general principle. You don't need to have different principles for different energies." So, in a way, Lorentz established relativity. Though Lorentz established relativity, Einstein generalized it into a universal principle. Right? So it has been through a lot of uh, uh, um, I mean variations, this series, but ultimately we have to give credit for Maxwell Lorentz, and Einstein. That should be the order because Maxwell related the electromagnetism. He almost removed the concept of ether. He transformed it into electromagnetism. Lorentz came up with transformations, and Einstein combined them all and came up with relativity, concept of relativity. Uh, the video is getting too long, so let us call it a day for now, and we'll meet next time. Bye.